All right. So, oh, I forgot to get connected. Okay, so we are looking at, again, this maybe deceptively challenging bell work here. So we have a random survey, 28%, blah, blah, blah. What is the degree of confidence that we can say that this margin of error, this confidence interval is correct? So really what we're saying is we're trying to convert our margin of error right here back into the degree of confidence, what confidence level we're at. So let's remember, first of all, that a confidence interval is a point estimate plus or minus a margin of error. And specifically for proportions, it's going to be a p hat plus or minus a z star times, our formula here is the square root of p hat times 1 minus p hat divided by n. And actually, I should even maybe show this in a different way. That might be our stat plus or minus our critical value times the standard error. Okay, so this calculation under the radical is for the standard error. And so we can figure this out. And really, we don't care about the point estimate. We do have it, but we don't care. So here's what I'm going to kind of boil this down to. Our margin of error, I'll just put the 0.04 because they're already telling us that it's a 4% margin of error. The margin of error plus or minus z star, and we don't know that because we don't know our confidence level. Square root 0.28 is our p hat. 0.72 is 1 minus p hat, and n is 450. So if I calculate that, and everyone can, hopefully you're kind of thinking through it at least to that degree. I know some people just kind of reflexively put 95% because that's, and I understand why you did that guess, but this actually requires calculations in order to figure out what the confidence level was. Okay, so I got 0.0212. So basically I have this. Oh, this shouldn't have been plus or minus, I'm sorry. That should have just been equals. Our margin of error equals this calculation right here, because this is our margin of error. And we already know that our margin of error is 0.04. So that shouldn't have been plus or minus. I'm sorry. But anyways, when we calculate this, we get z star times 0.0212. All right, so I mean, basic algebra right here, we can divide. So 0.04 divided by my previous answer gets me 1.8898. That's going to lots of precision right there, but we can simplify it down, we can round it off at the end. All right, and this is where we have to kind of think through it. I think this is a good question because it's making us think through a lot of statistical concepts. So the z star represents how far from the mean do we need to go out to capture X% of the data. Now we know that for 95%, so if it's a 90th percentile, then that's 1.645. If it's 95th percentile, it's 1.960. And you can think of it, if we have a distribution right here, here's the mean. We're going to capture 90% of the data, we have to go out 1.645, maybe this far out in both directions in order to capture 90% of the data. All right, now 95% would push us even further, maybe to right here. And then we get this extra little bit right here that would push us up to 95%. So these are our critical values. I just showed the positive ones, 1.645, and this is 1.960. So 1.8898 is going to be somewhere in between those two. So I know it's going to be between 90 and 95%. My only two options are these two, And the answer is 94.1%. Now, at this point, you probably have enough understanding. Like if you're able to get it this far, then you're probably good enough to say, well, 1.8898 is pretty close to 1.96. So it's going to be a lot closer to 95% than it is to 90. So that's why you might just deduce that it's got to be 94.1. But the other thing that we can do, remember, we want to capture we want to capture whatever data is between 1.8898 and negative 1.8898. So here's what I'm going to do. I'm just going to do, and I can do this because it's we're dealing with proportions, which means I'm using a normal distribution. I'm going to go out to negative 1.8898. That's a negative right there, and to positive 1.8898. Now I want to figure out how much data is captured. What's the area of that? So I'm just going to do a normal CDF calculation, and my lower bound is going to be negative 1.8898. My upper bound is going to be positive 1.8898. And when I do that, I get 0.9412 and so on. So there we can see that is representing 94.1% confidence. All right, so it started off as probably a problem. You're like, oh, I'll just do this in my head. Or I'll just do a quick calculation. And you realize that there's more to this problem than meets the eye. So it's good. It helps us kind of think through a lot of stuff. And at that point, we're good to go. We'll move forward. Hey, we took a test last Monday and we didn't meet since then. So we got to do some progress here. Look at this. We start all the way at Lee's Ferry. Can you believe that, figuratively? And we figuratively made it to Diamond Creek. How crazy is that? All right, so let's see what's going on at Diamond Creek these days. Got a couple of pictures. Yeah, you can see some boats probably taken out. So let's look at Google Sphere of what's going on with this. You can see there are vehicles down there. If you are not aware, it's one place you can get down to the canyon by vehicle. Popular takeout place, but we're not jumping off the river just yet. We're going to keep floating the whole way through. We got a lot more Grand Canyon. Okay, so not much to it as far as it goes, but nice little field trip. So there's our progress, just one more unit, guys, and we're going to wrap this up and we are going to get started with that unit today right here. And okay, I'm going to leave it on this screen for a little while. And this first part is going to be a very conceptual discussion. And you're going to need to think back to your Algebra 2 if you've done some pre-calc or calculus or whatever the case. But Algebra 2, of course, is sufficient. So you're going to have to think back to a lot of different types of functions that are out there. And before we do that, I want to remind you, this harkens back to our regression analysis with scatter plots. We're dealing with each dot. I'll just kind of give a brief overview. Imagine we've got a bunch of data that's sitting right here in a scatter plot. Each dot, we're going to focus on this dot right here. Each dot represents a single individual or participant or something that has two quantitative variables measured about it. And so the X and the Y of this represent whatever two variables they are, height and weight, age and IQ, whatever. So two quantitative variables that are being compared for lots of individuals, and we create a scatter plot. Ideally, it works out the way that we always like, where it's this nice linear scatter plot. We can just do a quick linear regression analysis on it. But of course, sometimes that's not the case. And where we were before, last time we looked at the stuff, we said things like, oh, well, if you get a weird trend like this, you just say, oh, well, that's not linear, and therefore it's not appropriate to use a linear regression. Okay, so we're going to amend that slightly, but in the end, we're going to talk about a lot of stuff that might get you really scared about what's coming up. I want to reassure you right now, we're not going to be doing super complex stuff, but we do want to remember some things. So let's say I gave you guys a data set that looked like this. All right. So if you had this data set, it's nonlinear. Okay, so we're comfortable with that. But what function would you use to model that data set to be a line of best fit? And when I say what function, I don't mean an exact equation, but what type of function would fit that?
Exponential.
Exponential, maybe? What else could it be?
Quadratic.
Quadratic, and we don't know, okay? So it could be exponential, it could be quadratic. A lot of times there's just very subtle differences, and you might have to try it both. For now, let's pretend it's quadratic, but maybe it's not. Maybe it is actually exponential. And this is all the data we have, so we don't know kind of what it does from this point. So anyways, let's pretend that this is quadratic and that the parabola that best maps that looks like that. Okay, so this is quadratic. All right, let's just go through and kind of identify and remember the different types of graphs that are out there in the world. So this could be quadratic. Now let's say that actually this was exponential. Then of course the difference, we're still seeing the data the same way, but what would actually be is something that looks like this. So that's what our exponential graph would look like compared to the quadratic. Now in the first what's the word? Quadrant, in the first quadrant of our graph, it doesn't look much different. We're comparing this to this. There's really not much difference between those two. Okay, so whatever the case, we've got two different functions that seem like it could work for that. What if we had this going on? Now, let me try this again. So what might you call that?
Like a square root function.
There you go. That could be square root. Is there any other function this could be? So let me just kind of talk about the square root because that's a good option here. A square root function is basically just a parabola that's turned on its side. So maybe this right here would represent our square root function. Again, we don't care about the specific function that maps this. We just care, oh, square root. And of course, that's the inverse of this function right here, which is a quadratic. You're really having to think back to your algebra 2 stuff. Now, what about, we had an exponential that looked like this. So the inverse of that would be a function that looked like this. And what do we call, if I erase everything except the two that matter? Nope, didn't want to do that. If I erase this and this, what would we call this function right here that remains?
Is that a natural log function?
Natural log, a logarithmic, and it could be natural log, it could be log base 10 or base anything. But yeah, it is logarithmic. So there you go. And we kind of just saw one of the main ideas. So if you imagine your inverse line, right, I'll just draw this right here. Your inverse right here, you should be able to reflect over that and end up with your inverse if you think back to your algebra. So this isn't a very good parabola, but if I reflect over there, then I'm going to get a square root function that looks like this. If I have, let me draw this again. If I draw my inverse right here, or sorry, my exponential right here, my inverse is going to be a logarithmic right here. So you can see that's just a reflection. So bottom line, your exponential, and I'll use the natural log base right here. So your exponential is going to be associated, I'll just put an arrow right here to say it's connected with kind of a logarithmic function. Those are the inverse of each other. And likewise, your parabola, which would be an x squared function or a polynomial degree 2, is going to be associated with the square root. All right, now let's see, are there other functions? There are some other ones here that are worth mentioning. What would a function that looked like this potentially be? Anyone remember seeing functions like that?
Exponential decay.
It could be something like that.
Is it
Yeah,
a rational function?
there you go, like a rational function. There you go. Where specifically, I'm thinking of this as like a 1 over x, but a rational function, certainly. And it could be exponential decay. Now, it could also, and this is not one, let me see, your exponential function takes on the form a times b to the x. I think that's right. Yeah, I think that's right. Because there's also another type of function called a power function, which is a times x to the b. You just flip these two, and a power function has this appearance to it also. Power functions are actually really, really interesting. Hopefully at some point in your math career, you learn about them, see how useful they are modeling a lot of things in the world. But anyways, so this is all kind of complicated. Not complicated, I don't want to say that. But we're getting into some functions that maybe some of you are hoping that we don't get further into it because it's not making you happy right now. So anyways, when we're dealing with these functions, here's the idea. Let's go back to scatter plots now. If we had a scatter plot that seemed to be maybe exponential, all right, we can't do a linear regression with an exponential trend. We need it to be linear. So the way that we can make it linear, well, if it was exponential, well, let's say this to make it simpler. Let's say this is quadratic. So if it starts off as some kind of a quadratic equation that models this perfectly, but we can't do linear regression with a quadratic, then, well, here's our solution. We can just take the square root of it all. All right, so I can take this data, I can take the x values here, or maybe the y value, let me think through. I think we could take the x values, but basically we could square root this, and I can just do the inverse of it. And what I'm essentially doing is taking my x squared and raising it to the 1/2 power. These cancel out, I'm left with x to the 1st power. And now I've got a linear function. So think about what's the inverse of what I'm seeing. The inverse of a quadratic is a square root function. The inverse of an exponential is a logarithmic function. And by kind of multiplying or performing an operation on the data that re-expresses it, I can turn it into a linear function or something that's modeled by a linear function. And I want to make sure it's clear. Let's say that this was quadratic. And what I did is I did a square root on all the x values. So to go from y equals x squared in some way, I did a square root of the x values. So now I end up with y equals x to the 1st. But what I have here is the square root of x and my y values right here. And what this will do is it will re-express the data. I'll do this in a different color now. So now I've got this data that might follow a linear trend. Now the data values themselves haven't changed. And so I'm going to have to kind of go back and reconvert. This might sound very confusing right now, but in the end, it'll make sense. So I took a quadratic, and I converted it into a linear. Now I can do a linear regression on the data. But then when I want to make predictions, my regression equation might look like this. Y hat equals a plus b square root of x. Now when I make a prediction, I have to remember I converted this to linear by taking the square root of my x values. So therefore, I need to factor that in whenever I'm predicting for y hat. All right, so this is the upshot. You're going to be looking at equations where you've got like log of y hat, or square root of x, something like that, because the data has been re-expressed. All right, so you do not have to actually do this. You can do it in the calculator. And in years, last year when I did this, we did actually go through the full process of it. But I'm just giving you what's essential, because here's what AP will expect of you. So let's kind of run through a few things. The simple rule for re-expressing is to identify the type of equation shown, whatever models the data, and transform it by the inverse of that. So bottom line, if you have an exponential, you want to do the log of y. If it's logarithmic, you want to do the log of x to convert it. You're not actually going to be doing this conversion. So this is, here's really all you're going to need to know about. If this has been re-expressed, your regression equation is going to look something like this. Maybe it was exponential. Now you're going to have log y in here, not just y hat, but log of y hat. If it's a power function, you're going to get two logs that you have to deal with. Okay. So in fact, it's not even in the AP standards for you to actually re-express the data yourself. You're not going to have to look at it, decide, oh, I want to do the log of this, convert all these x values into the log of that. You don't need to do that. Instead, you're going to be figuring out the predicted values of a regression equation that has already been re-expressed. So you're just going to need to do some algebra. And you're going to need to work with those log functions a little bit. So your homework tonight is one problem that looks exactly like this, except slightly different. All right, so not exactly like it, I guess. And let's go through. Notice this is a regression equation that's been changed. In this case, we got log of x. And for all these, we're going to evaluate it where x equals 2. So we're making a prediction when x equals 2. So we'll start with this one. This one's not going to be too bad. I'll just bring it down. Y hat equals 1.2 plus 0.8 times log of 2. You have this on your calculator. It's worth pointing out right now that when you just have log, you're technically doing log base 10. It's worth pointing that out in a little bit because we're going to come back to it. But my calculator has this function on when you hit log on the left side, it's automatically doing log base 10. Okay, so I'm going to do 1.2 plus 0.8 times the log of 2. And I got y, my predicted y value is 1.441. I can't just plug 2 into that, like without the log. I can't just plug 2 and calculate. I have to do the log of 2. All right, hopefully that one's clear enough. This, you will almost certainly see a question on your AP test, and you'll see one on your test in class regardless, that will have something re-expressed, and you're going to have to go through and calculate what's the missing value or what's the predicted value. So right here, the problem changes a little bit. Now I'm looking at B. Log of y hat equals 1.2 plus 0.8 times 2. We'll see this one a few times. When we plug 2 into this, we're going to get 2.8. But now we run into a problem. I've got log of y hat equals 2.8. Can anyone tell me what we should do in order to figure out what y hat equals?
Ten to the 2.8 power.
You got it. So this is where that log base 10 comes back into play. If it's log base 10 equal of y hat, well, we can kind of cancel this out in a sense by doing 10 raised to this power and then 10 raised to this power right here. So the log 10 and the 10 raised to that power cancel each other out. Y hat equals 10 to the 2.8 power. And your calculator can do that. This is another helpful hint on your calculator. Where it says log, the inverse of that is going to be the second function. So log, the inverse is 10 to the x. Where it says x squared, the inverse is square root. Where it says natural log, the inverse is e to the x. Okay, so 10 to the 2.8 power gives me 630.96. Okay. I want to go back and check something real quick. Make sure I didn't screw you guys up. I feel like I was saying something wrong. All right. Yeah, so if it was exponential before, we would do the log of the y values. It seemed right at the time. I wrote it wrong. All right. Again, we won't have to necessarily do that calculation. Okay, the next one. We've got two natural logs going on. Not a whole lot to it. So natural log of y hat equals 1.2 plus 0.8 times the natural log of 2. There we go. Again, we already have the natural log function on our calculator, so I can figure out the right side. I got 1.7545. You write down as much precision as you want, because now what are we going to do to get y hat?
E to the 1.7545.
There we go. We do e to these powers. Those kind of cancel each other out. Y hat equals e to the 1.7545. There's the answer. You just hit second natural log because that's the inverse of it. And I get 5.781. And you'll be in that ballpark depending on how much precision you put for the exponent. All right. Now D should be very, I'm going to go ahead and say it. Everyone in this class should be able to do D very easily. So if I've got y hat squared equals, when I plug 2 into this right here, I'm going to get 2.8. So what do I do with y hat? What do I do to get y hat on its own?
Take the square root.
There you go. Hopefully everyone knew that one like pretty quickly. I know with logarithms, it's not how our brains naturally think all the time until you get used to it. But you guys should be comfortable with square roots. So there we go. 1.6733. So you have some kind of a weird inverse square root function going on with this last one. So when I plug 2 in, I'm going to get 2.8. But I'm going to get 1 over the square root of y hat. What should we do? Any thoughts on first steps here?
Multiply both sides by the square root of y hat, and then it'd be 1 over 2.8 is equal to the square root of y hat.
Well, I like that thought. The problem with that is then we're going to have we're still going to have a square root of y hat. Oh, I think I see what you're saying. Yes, there's no problem with that. I was thinking of something else. Yeah, we can kind of multiply both sides. We want to get rid of that, this being in the denominator. So we can do that. Now, another thing we could do, because I know where you're going with this, we could just take the reciprocal of both sides just to shortcut it. Now, what you're going to be saying is we're going to have 1 equals 2.8 times the square root of y hat, and then move the 2.8 over. Or we could just do the inverse of both sides. So we end up with y hat, the square root of y hat equals 1 over 2.8. Take the reciprocal, which is essentially one step of doing the same thing. But you got the right idea. So I'm not trying to, don't take that as any negative way. So there we go. Now that we've got the square root of y hat equals 1 over 2.8, what are we going to do?
You do 1 over 2.8 squared.
There we go. Let's square both sides of this. And now I get y hat equals 1 over 7.84. There's the answer. Different ways you could approach this problem, but you should all end up with this right here. Hopefully everyone followed along with that one. If you have any questions on this, stick around, let me know. But keep in mind, again, when you re-express data and now you have this nice linear trend of your data, and sometimes it works like perfectly, where you almost end up with a perfect correlation, you're not saying, oh, my X's and Y's are correlated perfectly now. What you're saying is that maybe your log of X is perfectly correlated with your log of Y. Okay? So keep in mind that we have changed our X and Y scales to logs of numbers. And actually, I'll just get rid of this. Let's say that it was only log of X. Okay, so that's why we still have to do these conversions when we're making predictions. Okay, hopefully I've said enough on that. And now we're going to talk about our project. Before we do, are there any questions on stuff we talked about today? All right, I encourage you to look over chapter 10. There are some other things in there that go beyond what the AP test is going to expect of you, including stuff like ladder of powers and things like that. It's worth kind of looking and conceptually getting the idea, but just make sure you can do stuff like this. You understood some of the conceptual things we talked about. All right. Oh, the other thing, make sure that you review chapters 7 through 9, which are all about scatter plots and things like that. It's going to make inference. When we start that tomorrow, it's going to make a lot more sense for you. You need to remember how we find the slope. What does the slope and the intercept mean for our regression equation? Correlation, the correlation coefficient and your R squared coefficient of determination, just kind of review that stuff. If you can make sense of all of that, then you're good to go. All right, let's talk about the project now. And keep in mind, there are going to be some bullet points on this that you might want to remember. And this presentation is available online. So don't bother copying anything down. Just if there's something you wanted to come back to and look at this, you can find it there. Okay. So the basic idea of the project is you're going to conduct research for a problem of your choice. And the overview, very basically, is you're going to select a problem that can be investigated using an inference test of some kind. You're going to collect data using online sources to create your sample or samples so that you can conduct the appropriate inference test. You're going to report your conclusions, and at the end, you're going to record a short presentation to discuss your project, the calculations you did, your conclusions, and so on. Okay, we're not going to talk much about the presentation today, but we will talk about that more later. Okay, so this is what's due this Friday, and this is where you need to kind of be focusing today, which is why we're not worried about the actual recording of your presentation. So a problem statement will be due on Friday. There's no assignment on Canvas yet, but it will be up there before too long. Okay, in the problem statement, you should clearly indicate what your problem of interest is, a hypothesis related to the problem, the inference test you will use to test your hypothesis. And if that sounds like a lot to put in, one sentence can cover all three of those. So here's a couple examples of that. To state what the problem of interest is, a hypothesis related to the problem, and the inference test. I will use a two-sample t-test for a difference of means to test my hypothesis that the average temperature in Flagstaff has increased compared to 30 years ago. Or I will use a chi-square test of homogeneity to test my hypothesis that high schoolers are playing different types of video games today than they did 10 years ago. So we have, of course, we do have the linear regression inference, but we're learning that this week. I don't expect you to use it, but you have your 1 and 2 sample T and Z tests. You've got your chi-square tests for independence, homogeneity, goodness of fit. So you've got different inference tests you can use, but you're going to need to obtain your own data rather than just, have a problem with it already there. This is going to be time consuming. Now I put right here, make sure that you meet the conditions for inference, and I will put a little star beside that because you can just add a little caveat to your analysis if you can't quite get enough data. So for instance, remember, if you're going to do a two-sample t-test, or sorry, a two-sample z-test for difference of proportions, you've got your large counts condition that must be met. All right, so I've got N1 times my pooled proportion has to be greater than or equal to 10. I've got N1 times 1 minus my pooled proportion has to be greater than or equal to 10. I've got to do the same thing for N2, with the pooled proportion. All right, so you're going to want to try and collect enough data so that you actually meet this condition. If you can't quite do that, because in some cases it can be hard to collect data, and we're going to talk about that in great detail in a little bit. But if you can't quite get enough, you can add a caveat that says, I found some really good data. It wasn't enough for me to meet conditions for inference. So ... take my results, with a grain of salt. So you can add something to that in your final report. And the main thing, don't procrastinate on this. It might seem like it's pretty straightforward. Once you have your data, it should be very straightforward. You just pick the proper test, you take your data, you're gonna have to crunch the numbers, maybe get some means or proportions, or lay out your, if you have a two-way table that you have to create because you're doing a chi-square test of independence, you're gonna have to crunch the data to get your counts to go in each one of these and figure out your expected counts. All right, so there's all kinds of stuff that you'll need to do. But once you have that, it's pretty straightforward. It's like any inference problem. But you're going to have to collect the data, and this is going to be the time-consuming part. So here are some possible data sources. Data.gov is just a clearinghouse for all kinds of data. You're going to have to parse through that. There's a lot there. Census at School. So this I will show you. This might actually be what a lot of you end up using for your data. National Climatic Data Center. I'll show you an example of some of these, like Census at School, National Climatic Data Center we'll look at. Kaggle we'll look at. Again, you don't need to copy these down, just come back to this PDF later. Google Trends and Google Public Data. I'll tell you, Google Trends you probably won't use, but maybe you can figure out a way to make it work, and I'll show you what that looks like. Google Public Data is just kind of searching Google for a lot of public data. But I think what a lot of you will end up doing once you decide on what kind of problem you're going to work on, just a web search. And I have a couple of tips just as you're getting going. Think through the problem of interest and identify the data that you need ahead of time so that your web search can be very like pinpoint accuracy. Like you can type in exactly the search terms that you need. Because if you just are like vaguely, I'm looking at cancer data, let me get some cancer data. That's going to be so broad of a search term, you're not really going to have success tracking down any data. But if you know specifically what you're looking for, you can kind of pinpoint a little better. This is going to be the hardest part of the project. I'm giving you a week to get this done and turn it just the kind of the explanation of your project done. So you might need to spend 3 of the days trying to find the data for your project. Okay, and this is kind of a last resort. I really want you to put in a lot of effort to find the right data that you can. But if you cannot find the data that you need, then look at what data you can obtain and change your project to fit the data. All right, you wouldn't do this as a researcher in the real world, but you'd be able to collect data. I'm not asking you guys to collect data by doing surveys. I want you to just find data that's already available. So if you can't find the data available to help you with your problem, just change what your problem is. Okay, but you still need to make sure you're using an inference test to test your hypothesis. Okay, now before we finish off class, I wanted to show you some examples. And here's some that I didn't mention, but NASA has what's called Earth data, lots of data sets. If yours relates to that, you might end up wanting to search this site. Pew Research Center has a lot of almost census type data. So, but they do a lot of different things. It looks like you need an account, but I'm assuming it's free. Some of these places require accounts if you're going to download data. This is the World Health Organization, and you can see probably just a small amount of the data they have available. You can do a more focused search and find stuff there if you're going in the health direction, medical direction. This is Google Trends, which what you can do with this, and there might be other things you can do with it, but you can basically look up search terms, and it gives you this time plot that shows where it was most popular. And they do this kind of on a relative scale. So it's relative to the most popular. So apparently Diwali was the most popular search term in October 2019. And so it gets this 100 rating. And everything else is relative to that. So honestly, I'm not sure if this is going to be helpful for you guys, but you can see it's kind of fun to play with regardless. So Google Trends is one you can kind of play around with. Like here, we can do something real quick. We can see like what's more popular. Which search term is more popular? I'm going to just get it down to 2 over the last, what is it, like 15 years or something? 16 years. So it was Donald Trump or was Beyonce a more popular search term? And it looks like Donald Trump has been more popular over the last, well, you can see not very popular. And then I wonder why he got so popular around this time. All right. So now, I mean, that's kind of just fun to play with, but we won't take any more time. Here's Google Public Data. And again, I haven't played around with this too much, but you might find that useful. All right, this is the National Climatic Data Center, and you can get some local climate data. And I will show you some of that in just a minute. You can just go in, like if you're interested in data on Flagstaff, this should pop up with stuff. I think I need to reload the page, but basically you can pinpoint it down and you will have to request to download the data by giving an email, and it'll send you the email with the link and everything, but it's free. So I'll show you, I downloaded some last night. Here's data.gov. You can see all of these data sets found. Census at School. This one's, I'm going to come back to this one. That's more a National Climatic Data Center. But notice that, if you're going in that sort of global warming or climate change or other directions related to weather, you can see all kinds of different options. All right, I'm not trying to get too much into the weeds here. So we got Kaggle, lots of data sets here. Notice that, and this is when I looked up last night just for fun, like if you're into baseball and you wanted to look up data on pitches, like are pitchers throwing the ball faster than they did many years ago? Now this is pitch data from the last, or 3 of the last recent years. It's a huge data file, 370 megabytes. You probably don't want to download all that, or you could. And anyways, you're going to have to kind of parse through and figure out what this data means. So here's start speed. So now this is going to show in miles per hour. So this pitch right here was 92.1 miles per hour when it left the hand, and so on. So you can kind of parse through it. Another thing you need to do is cite where you got your data. And this is kind of why I wanted to show this. I don't want you to just write, I got this data from Kaggle.com. Notice right here in the description, it says that the data was scraped from this website. So if I click on that website, actually haven't been here. Oh, page not found. But you can still cite it, that it came from this website, even if it's not active, that's what it says. So the cite where the data came from. All right, if you have questions on this, stick around. Census at School is kind of like a census that's taken by high school and elementary school students and middle school. So this might be where you end up getting your data. You can select how big of a sample size you want. And notice that, actually, let me go back to the beginning. There is the random sampler right here. So that's what I went to. So the random sampler, it will randomly pull from its database. You don't need to do anything too complicated here. Like if you know that you need 500 to meet your conditions for inference, well, I want a sample size of 500. I'm only interested in students in Arizona, and I'm only interested in seniors, both genders, data collection year. I'm happy with all these years, the last 10 years it looks like. So then I can do that, and look, I have some data ready to download. All right, so Census at School is a really good option. So now let's look at the census data. So I wanted to show you what data looks like to show you that it's going to be a little bit of a, oh, this is the wrong one. I didn't want census, I wanted the climate data actually. All right. Sorry about that. All right, so here is the climate data, and all right, let me scroll back up to the top. You're gonna have to kind of look at this. It doesn't come in like very neat and user-friendly. So if you were gonna compare temperatures, you're gonna kind of need to look through all these. And if you do that, you can kind of see what all the different headings are. Anyways, I want to know the temperature, daily average. Well, temperature, there's dry bulb and wet bulb. Just, if it's something like this and your data set could be really weird, just kind of keep it consistent. I'll just look at the dry bulb temperature. So on January 1st, and I can see the date way over here at the end. This is January 1st, 2019. On January 1st, it was 9 degrees average temperature. And you can kind of randomly sample from the days, and you'll have to skip around a little bit, but you can get it. Okay. So there's some climate data, and yeah, I mean, there's just a heck of a lot here. So just keep in mind, this is why I'm saying this is gonna be the most time-consuming part of your project. All right, I'm gonna go ahead and close that. Now the other one is census data. This came from Census at School. And these are kind of a mix of all high school age students from Arizona. And I got some from New York also. I just picked a random thing. There's so much data right here. All right, so we've got arm span. We've got the mode of travel to school. We've got favorite physical activity. So we've got categorical data, and we've got some quantitative data. So from here, you can kind of use this data to figure out what you want your project to be. Like, here's hours doing homework. So maybe you want to say, is there a difference in the amount of times people spend on homework, high schoolers spend on homework in Arizona versus New York? So now I can say, I'm going to take a random sample of the Arizona students and a random sample of the New York students, and then I will, have that data set to compare. If it's categorical, maybe we go back to, or was it the favorite physical activity? You could do categorical. So you could do, maybe do a chi-square test of homogeneity. All right. So, or maybe you do how you set it up as chi-square test of independence, just depending on what your problem is. So bottom line, you have all kinds of options. I will stop sharing. Actually, I'll go back to the original share. So there we are. So that is kind of an overview of what you need to be working on for your project this week. It might take you longer than you think, so get started on it tonight. All right, the other stuff for tonight, review chapters 7 to 9, just to kind of get the idea again of scatter plots and linear regression. We're gonna look at chapter 27 tomorrow. Your homework is only one problem, and that's about it. If you have any questions, you can stick around. Otherwise, you can have a great day, and I will see you tomorrow.